The last problem on exam number 1 for spring 2015 is the integral e to the 2x dx over e to the 2x plus 4 e to the x plus 8. Now, this looks like kind of a weird integral, but she does give you a little hint early on. She says begin with an appropriate u sub. So when I'm looking at something like this, I don't really see anything initially that makes me think that a u sub would be even useful. If I try to assign u equal to the entire bottom, I end up with a really weird expression because e to the x doesn't derive out like x squared or something would. It just keeps going. And having this e to the 2x, having these be the same power is pretty weird in that case. But what I can do is by looking at these terms, I know that e to the 2x is just e to the x quantity squared. So what I can actually do is if I just say u is equal to e to the x, and du would just be e to the x dx, accordingly, I can go through and at least try to start some kind of substitution here. So I have an e to the 2x dx up top. Now if I want to account for that, what I would have to do is I would kind of have to write it as e to the x times e to the x dx. Now I know e to the x dx in this case is equal to du. All I would have to do is just account for that extra u term that's up there. So I end up getting u du on the top, and here I'm just plugging in terms basically. So u equals e to the x, u squared is e to the 2x in that case, according to this substitution, or this expression that we wrote out earlier. So I have u squared plus 4u plus 8. Okay, cool. So now, we've gotten to this part right here. We've done our u substitution, but now we need to figure out where to go from here. When I take a look at this, integration by parts doesn't really look like a good idea. There's no trig functions. Partial fractions might be okay, so maybe partial fractions could be good. We could also do trig sub. Trig sub, for that to be able to work, remember we need to get it into some kind of form of like u squared plus a squared minus u squared minus a squared. In this case though, as this polynomial term, it's not really going to work. So the first question I ask myself is this bottom factorable? Is it a perfect factor of something? Well, the only factors of 8 that I know are 8 and 1 and 2 and 4, neither of which add together to just get 4 by itself. So this is a non-perfect term. So what we can do is we can complete the square and maybe get it into a form that we can apply trig substitution for. Remember, if you're completing the square, you probably don't want to bother with partial fractions because it's going to be in kind of a weird form and there's no real way to split it from there. And with partial fractions, you have to be able to split it into perfect terms. So, by focusing on this, 4 divided by 2 is 2, 2 squared is 4. So to complete the square, I'm going to add 4 and subtract 4 from the term. So I end up getting u plus 4 plus 4 plus 4u plus 4. This is my perfect square. This becomes u plus 2 quantity squared. 8 minus 4, that's just plus 4. So now I can write this integral in a different form once again. So I have u du, I have u plus 2 quantity squared plus 4. Okay, so now I know it's in this form. What I can do now is it's in a perfect place to do trig substitution. So let's go ahead and do a trig substitution. U plus 2 is my term. So in this case, u is going to be treated as the x term. So it is just u squared plus a squared. So I still use a tangent theta, which means that now I need another substitution. And I need to figure out what the term is in front. My a squared is 4, so this becomes a 2. So u plus 2 is equal to 2 tan theta is going to be my substitution. And of course I want to take the derivative. The derivative in this case is going to be 2 secant squared theta d theta. Okay, so we're almost good, except for one last thing. I have a u term up here. It isn't really helping anything out. It's only kind of making our lives more difficult, but we still have to account for it. So what I can do is I can subtract this 2 off. I have something to plug in for that top part. So now, u minus 2 is equal to 2 tan theta minus 2. So I can go ahead and plug that in. And that's multiplied by 2 secant squared theta d theta. So this term is distributed throughout. And on the bottom here, I have u plus 2 quantity squared, which we knew was 2 tan theta. So if I square that term, I end up with 4 tan squared theta plus 4. I pull out a 4. Tan squared theta plus 1 is equal to secant squared theta. And we're good. So it looks like I could do some simplification here. Secant squared can cancel. I have a 2 over 4. I can also pull a 2 out of both of these terms. I can turn this into tan theta minus 1 times 2 on the outside. 2 times 2 is 4. Over 4 is just 1. So let's rewrite it one more time because we did a lot of simplification here. It looks like I have ended up with a tan theta minus 1 d theta as my integral. Okay, so now we just need to figure out how to integrate these terms. Well, I can integrate tangent of theta. Tangent of theta, well, again, it has two forms. It has natural log of secant, and it also has negative natural log of cosine. In the case of exams, using either one won't matter. Dr. Chewy seems to like the secant one a little bit better, so I'll stick with that one for now. So the integral of this is equal to natural log of secant of theta minus, if I integrate 1 with respect to theta, I get theta. Theta, and of course I have a plus c. Okay, good. So now we've ended up at a solution in terms of theta. But now we need to take a step back. We need to figure out what all these terms are. First in terms of u, and then in terms of x. So the way we go from here to u is we write out our triangle. So I'm going to go ahead and make myself a little room here. I've already figured out what these are. And I will rewrite the substitution we used. So in this case, we did end up using u plus 2 was equal to 2 tangent of theta, and du is equal to 2 secant squared theta d theta. Okay, it's important because we need to know this to make our triangle. So if we're going to make our triangle, it's not really that big of a triangle. Let's be a little bit bigger than that. Just a little more room. Okay. There's my angle, there's my right triangle. So now, in this case, I have tangent of theta is equal to u plus 2 over 2. That's tan theta. Tangent is equal to sine over cosine, which is opposite over adjacent. That means that my opposite is going to be u plus 2, my adjacent is going to be 2. And I can figure out what this side is going to be by Pythagorean theorem. So this would be u plus 2 quantity squared. So I end up getting u plus 2 quantity squared plus 4 underneath the square root, which, if I go back through and plug in for that, I should get exactly what I started with my original substitution, which is the square root of u squared plus, so this would be 4u plus 8. So this is actually what this is equivalent to. Okay, good. Now, I need an expression for secant. So to get an expression for secant, I look at hypotenuse over adjacent. So that ends up leaving me with the square root of, so I have square root of u squared plus 4u plus 8 over 2. Okay. And now I need to figure out, let's see, so I have this term right here. That's good. Now I need to figure out an expression for theta. So when I'm looking for an expression for theta, I want to look back at my original substitution and try to get theta by itself. So if I have u plus 2 over 2 equals tan theta, theta is equal to the arctan of u plus 2 over 2. that should get me what that angle is. So now I have an expression for that. That's minus arc tan of u plus 2 over 2. And I have a plus c. Good. I have expressions for all that stuff. I can go ahead and now I can actually sub back in for my original substitution, which is u equals e to the x. So I end up getting natural log of square root of e to the 2x plus 4 e to the x plus 8 over 2 minus arc tan of e to the x plus 2 over 2 plus c. Okay, we're good. So this would be a perfectly acceptable final answer on a free response. But if you'll notice, this term matches on the answer key, but this term looks a little bit different. So what they did there is they just did a little bit more algebra. And what they're doing is they're, first off, splitting this natural log. So remember, if I have natural log of a over b, that's equal to natural log of a minus natural log of b. So I can rewrite this first term as natural log of square root e to the 2x plus 4 e to the x plus 8 minus natural log of 2. This natural log of 2 is a constant. It's like 0.69, negative 0.69. This term can get added into the plus c, so you actually don't need to write it out. So remember, c plus any constant term is just c. So if I had c plus 1,000 or something like that, it's still just plus c. So you don't need to write it in your final answer. Now again, kind of an extraneous step. You don't need to do it to get full credit on a free response. I'm just trying to explain how they got to the final answer in the answer key. So this ln of 2 gets added into the plus c. Now the last thing they're doing is, remember, if you also have natural log of a to an n power inside like that, you can bring the power down in front and just write it as n times natural log of a. So again, in this case, they have this e to the 2x plus 4 e to the x plus 8 all to a 1/2 power, because that's what a square root is. So what they're going to do is they're just going to pull that 1/2 down, and it becomes 1/2 natural log e to the 2x plus 4 e to the x plus 8. As that answer, you have the minus arctan, and you have the plus c. So technically, this added together would be the answer that they have in the answer key. But again, what we had before with this natural log of square root of e to the 2x plus 4 e to the x plus 8 over 2 is perfectly acceptable, and you would still get full credit if you left it like that. So, and that leaves us with the final answer to free response number 3 and the end of the exam.
The Teaching Center, UF's Learning Resource Center.